Hello everyone. On this video we will look at simplifying rational exponents using rules of exponents. Okay, but first we're going to cover converting radical symbols to exponents. Alright, so let's say if we had our square root of a. Okay, so we know now that when there's no index given, you automatically assume that index is a 2. Okay, now to convert this to an exponent, that's just a to the 1/2 power. Same with if you have a cube root of a, that would be a to the 1/3 power. You have a fourth root of a, that would be a to the 1/4 power. And if you have the fifth root of a, that could be a to the 1/5 power, and so on and so on and so forth. So really, when you have the nth root of a, it's just a to the 1 over whatever the index happened to be. Okay, that's how you convert from a radical symbol to an exponent. Okay, so now let's review our rules of exponents. Alright, so first, if you remember, you had your product rule, which gives you the formula x to the power of m times x to the power of n equals x to the m plus n. Okay, so for example, let's say if you had 3 to the 4th power times 3 to the 7th power. Okay, as long as your bases are the same, okay, they're both have a base of 3, you just add your exponents. So it's 3 to the 4 plus 7, which is 3 to the 11th power. Okay, so now let's look at the power rule. Which states that if you have x to the power of some value m, and that whole thing is raised to the power of n, some value of n, and that's x to the m times n. Alright, so for example, if we had x squared to the 9th power, then that would be x to the 2 times 9, which would be x to the 18th power. Okay, now what if we had the quotient rule? Which gives us x to the power of m over x to the power of n, which is equal to x to the m minus n. Okay, now an example of that would be, let's say if we had 8 to the power of 30 over 8 to the power of 27. Okay, once again, our bases are the same, so we just subtract our exponents. So that's 8 to the 30 minus 27th power, which is 8 to the 3rd power. Alright, so we're going to go ahead and continue this on the next page. paper down. There we go. Alright. So now we're going to look at the power of a product rule, which states that if you have, let's say, some x times y to the power of m, you're just going to distribute that exponent to both of those factors. So that's x to the power of m times y to the power of m. Alright, so for example, let's say if you have 7x squared. Okay, so that would just be, you just distribute that squared to both of those. So you have 7 squared times x squared. Okay, we know 7 squared is just 7 times 7, so that would really give us 49x squared. Can't really simplify the x squared because it's unknown, so we just leave it like that. Okay, so now we want to look at the power of a quotient rule, which gives us, say, x over y to the power of m. And just like the power of a product rule, where we distribute the exponent to both of those terms, same thing here, we just distribute the exponent to both of those values. Okay, so for example, let's say if we had x over 5 to the third power. And that's just going to equal x to the third power over 5 to the third power, which is equal to x to the third power, and 5 to the third power is 5 times 5 times 5, which is 125. Okay, so we have also rules for when you have exponents of 1 and 0. Okay, so when you have an exponent of 1, x to the power of 1 is just going to equal whatever that value of x is. And x to the power of 0 will always equal 1. Doesn't matter what the number is. If it's raised to the power of 0, it's going to equal 1. Okay, so for example, if you have 85 to the first power, that's just going to equal 85. Okay, if you had 2 million to the first power, it would just equal 2 million. Okay, and also, let's say if you have, for example, 298 to the power of 0, then that's just going to equal 1. Okay, now every once in a while this doesn't really make sense, so I'm going to go over a quick proof to show you why this is always the case. So let's say we have some value of x. It could be any number, and that's why we're using x, any number raised to the power of 0. Okay, so instead of 0, we can make that x to the m minus m. Okay, remember, anything minus itself is just going to be 0, so it could be 3 minus 3, 8 minus 8, 20 minus 20, just m minus m. Okay, now if you look at the power of a quotient rule, well, not the power of a quotient rule, but the quotient rule on the previous page, if you have x to the m minus n, that's equal to x to the power of m over x to the power of n. So if you have x to the m minus m, it will be x to the power of m over x to the power of m. So we're going to convert this to be equal to x to the power of m over x to the power of m. Okay. We already know anything divided by itself will always equal 1. That's why x to the power of 0 will always equal 1. Anything to the power of 0 will equal 1. Alright. Now we have our negative exponents. Okay, so that means if we have x to the power of negative n, that's going to equal 1 over x to the nth power. So if you have a negative exponent, just move it down to the denominator, and your negative exponent becomes positive. And if you have 1 over x to the negative n, if you have a negative exponent in your denominator, you're just going to move that up to your numerator. So it's x to the power of n over 1, which is just x to the power of n. Alright. So, for example, for this one, let me move that up a little bit. Kind of separate that. If you have 3 to the negative 4th power, you would convert that to 1 over 3 to the positive 4th power. And let's say if you have 1 over 8 to the negative 2 power, then that would just become 8 squared over 1, or just 8 squared. You really don't have to put it over 1 if you don't want to. You could just make that 8 to the negative 2, make it 8 squared. Alright. Okay, so moving on. Okay, now when we're simplifying, this is actually a very important rule. Okay. If we know that the nth root of a is equal to a to the 1 over nth power, then the nth root of a, if you raise that to the nth power, those two will cancel each other out, which is equal to a. Okay, so if we do a quick proof of that one, and again we know the nth root of a is equal to a to the 1 over nth power. So that means if we have this portion of the rule here, so if we have the nth root of a to the power of n, we know that our nth root of a, we can make that 1 over a to the 1 over nth power. So that's a to the 1 over nth power raised to the power of n. Okay. Now, using the power rule, that becomes a to the 1 over nth power times n. Or we can make that a to the 1 over nth power times n over 1, which is equal to a to the n over nth power, which is a to the first power, since anything divided by itself is equal to 1, which is just a. Okay, so we know that this will equal a. Okay, so let's say, for example, move that up a little bit. If you have the cube root of 8, and let's say we raise that to the 3rd power, it's going to equal 8, because those two will cancel each other out. Okay, so what if we have the cube root of negative 27x to the third? Okay, now if we convert this, that would give us negative 27x to the third power. And instead of using the radical symbol, we convert that to an exponent. So we make that to the 1/3 power. Okay. Now if we remember our power rule, or power over product rule, we just get that exponent and distribute it to both of those factors. So that would be negative 27 to the 1/3 power times x third to the 1/3 power. Okay. Now if you remember the cube root of negative 27, I'll just go ahead and make a little side note for that one. The cube root of negative 27 is actually equal to negative 3. And that's simply because negative 3 times negative 3 times negative 3 equals negative 27. Gotta clean that up just a little bit. Okay, so that's equal to negative 27. Okay, so we end up with negative 3 and x to the third power times 1/3. Remember, if we wanted to, we can just make this x to the 1/3 times 3 because it's our power rule. It's just x to the first power or just x. So you end up with negative 3x or 3 times x. Okay, so let me give you another example. Okay, let's say, for example, you have square root. Remember that 2 probably won't show up in a problem like this. I just kind of wrote it there. Times y plus 4 squared. Okay, remember, you have an even index. So whenever you have an even index, your radicand has to be positive. Okay, so these two cancel each other out. So your answer would be y plus 4, but it would have to be positive because you have that square root. Okay, so if you had the square root of x squared, then your answer would be absolute value of x. Because whatever that x value is, it would have to be positive. Okay, so make a quick note here. Going right to that index. So even index means the radicand has to be positive. Uh-oh. Straighten that a little bit. There we go. Okay, so every once in a while you'll run across a problem where you have to put that absolute value. Alright. So now let's say if the letters M and N represent integers. Okay, so far we've been having our exponents with 1 as the numerator. But sometimes you'll have a different value as your numerator. So let's say if you have x to the, instead of 1 over n, let's say m over n. Okay, so the first thing you want to do is you want to take your numerator and move it to the outside. So that would be x. You're going to take your denominator and make it 1 over n and move your numerator to the outside. Okay, and that's because if you go ahead and use the power rule, then if you multiply those two together, you end up right back here. Okay, so we know you can have it this way, or x to the 1 over n is just the nth root of x. And that's going to be raised to the power of m. So you can write this either way. Or let's say you have x to the negative m over n. We end up with the exact same thing. The only difference is, since that's a negative exponent, we move it to the denominator and make it positive, which ends up giving us 1 over the nth root of x to the power of m. Alright, so let's say, for example, if we wanted to simplify, let's say for problem A, we have 32 to the 2/5 power. And let's say for problem B, you have 81 to the 3/4 power. Okay, so we're going to solve both of those using rule 1. Okay, so for problem A, if you have 32 to the 2/5 power, remember you're going to take your numerator and move it to the outside. So you have 32. Since your denominator is 5, you're going to make that to the 1/5 power and raise that numerator to the outside. Okay, so 32 to the 1/5 power, remember that's just the 5th root of 32 squared. Okay, so we know the 5th root of 32. We know that 2 times 2 times 2 times 2 times 2 equals 32. So we know the 5th root of 32 is equal to 2. So that gives us 2 squared. And 2 squared is just 4. So 32 to the 2/5 power is equal to 4. Okay, so let's try that again with B. And a little line there. So problem B, we have 81 to the 3/4 power. And again, we get our numerator, and we move that on the outside. So you have 81, since our denominator is 4, that's to the 1/4 power, and we move our numerator to the outside. Okay, now 81 to the 1/4 power, we know that's just the 4th root of 81, and we still have our 3rd power up there. Okay, so what number do we multiply by itself 4 times to get 81? Well, that would be 3. So we know that 3 times 3 times 3 times 3 equals 81. So the 4th root of 81 is equal to 3. And that's still to the 3rd power. 3 to the 3rd power is 3 times 3 times 3, which is 27. So 81 to the 3/4 power is equal to 27. Alright. Go ahead and do one more example. What if we wanted to simplify? Say for problem A, we have negative 64 to the 2/3 power. And for problem B, we have negative. Now the negative is on the outside of the parentheses here. Say 1/25 to the 3/2 power. Alright, so now we're going to look at the difference when the negative is inside the parentheses and outside the parentheses. Okay, so when you have the negative inside the parentheses, like in problem A, you have negative 64 to the 2/3 power. We're still going to get that numerator and move it to the outside. So here we're going to have negative 64, and since that 3 is in the denominator, that's going to be to the 1/3 power. Now our numerator, since we already have parentheses, you usually use brackets here. That numerator goes right on the outside. Okay, so this gives us negative 64 to the 1/3 power. That gives us the cube root of negative 64 if you wanted to write it as a radical. And we still have that squared. Okay, now remember, this is an odd index, so this can be negative. So really all we have to do is remember that negative 4 times negative 4 times negative 4 equals negative 64. So the cube root of negative 64 is equal to negative 4. And that is still squared. Now negative 4 times negative 4 gives us 16. So negative 64 to the 2/3 power is equal to 16. Alright, so for problem B, we have negative 1/25 to the 3/2 power. Okay. Now remember, this negative is on the outside, so you don't have to calculate it like you did this one. The negative just kind of follows you, kind of like negative 1 times this. So it's still negative. Now remember, we're going to distribute that 3/2. Okay. Now the thing is, 1 to any exponent is always going to be 1. It doesn't matter what the exponent is. 1 to the power of anything is always 1. So that one's going to be very easy. So we have negative, and we have 1 over, now 25 to the 3/2 power. Remember, that denominator is 2, so that becomes an index of 2 to the 25th power. And that's going to be raised to the 3rd power. Now, even though we know the square root of 25 is positive 5, okay, so that's negative. Okay, so you have 1 over 5 to the 3rd power. Okay, so that's going to equal negative 1 over 125, and we can actually drop parentheses at this point, so it's negative 1 over 125. Alright, so hopefully this has made sense.